Students, in today's class we will be learning about Kirchhoff's laws. When it comes to simple circuits, we can use Ohm's law to analyze the circuit, isn't it? So we have a few of the components, and a simple circuit if we have, Ohm's law is sufficient to calculate the output current and the voltage drop at the output or load. All these things can be found out of the circuit, can be analyzed very easily using Ohm's law. When it comes to some complex circuits, in the sense some huge circuits, when it comes then only Ohm's law can't be used to analyze the circuit or to reduce the circuit. So then only using Ohm's law will be very difficult to analyze. So then the thing comes is what? Kirchhoff's law. Kirchhoff's law let us to reduce the complex circuits or to analyze the complex circuits with the help of Kirchhoff's law, and also we can use Ohm's law both together to analyze or to reduce or to solve the huge complicated circuits. Now this Kirchhoff's laws were given by Gururaj Kirchhoff. So as a scientist, so simple scientist, we give these laws, or we can have two of the laws from Kirchhoff. And before going to Kirchhoff's laws, we have to understand some of the things, some of the terminologies which will be used. So what first thing is what? Circuit. So people are aware of circuit. What is circuit? Circuit is what? Interconnection of your source and all the circuit components to make a path for the electric current to flow. So that is called as what? Your circuit, isn't it? Yes. So now comes to node. Second thing is what? Node. What is node? Node, or we can also call it as what? Junction. So we can say node, or also we can call that node as what? Junction. So it is where the current divides. So current, we have a junction. Junction in the sense it is a point where the current divides. Such point is called as what? Node or junction we call it as. Okay, so it is the point where the current divides in the electrical circuit or electronic circuit. Okay, so in an electrical circuit or electronic circuit, wherein the current divides. Okay, so it is the junction, or it is the point where the current divides. So that is what junction or a node we call it as. Okay, so for example, I have taken a circuit over here. So where we have Vs, source voltage, and we have four of the resistances R1, R2, R3 and R4. So this is a resistive network. Resistive network in the sense like what's that? Resistive network or resistive circuit we can call it as. Why it is called as resistive circuit or the resistive network? Because it has got out of other than voltage source, so it has to be there. Rest of the components, all of the components in this circuit is what? All resistors. Okay, so it has got four resistors and nothing else it has got. Okay, we have voltage source and four of the resistors we have. So I can call this as what? Resistive circuit. Okay, so it is comprising of all the resistors. Okay, so we have four of the resistors connected, and here you can see I have named a few big points. Okay, so here we have something named as what? A, this is B, this is C, and this is D. Okay, so I have taken 4 points. I have named them as what? A, B, C, D. Fine? Yes. So now we will see. So what is a node? What is a node? We will see here. Okay. So node is what? It is the node or junction we can also call it as. It is where the current divides. So when there is some current flowing, where the current divides, so that point is called as what? Node or junction we call it as. So here we have applied some voltage Vs, because of that some current I flows. Okay, fine. So here the current I is coming here, and after this the current flows because of this voltage given. The current starts to flow here. It flows from here, and it goes through what? Resistance R1, and resistance R1 it goes and it comes here. It comes here, and after this point B. Okay, so what happens here is, so the current here it comes and here it divides, because both the sides it has got resistances. So the current which flows from point A through resistance R1 and it comes to point B. Here it has got 2 options to flow. Isn't it? So this is the point where the current again, like current is going to get divided. Okay, so here the current comes and here it gets divided. Okay, for example, if I take this as what, some I1 which is flowing, now I can name it as what, some I2, and this as what, some I3. Fine? Is that okay? Yes. So the current I1 which comes here, and at this point B, it has got two ways to go. So both the ways it will go depending on the resistance value. If like in this direction I have one resistor R3 and we don't know how much value it has got. It depends on the value of resistance. So here it has got one resistor R3 and here it has got two resistors R2 and R4 which are in series. Okay, fine. So now it depends on the value of resistances, the current more or less which is going to flow. Okay, so here the current at this point, the current divides into what, I2 and I3. Okay, so again after this, so here I2 comes here, I3 comes here after flowing from here. And at this point again the current is going to what? Combine. Isn't it or not? So at this point the current has divided, and again after this the I3 has come from here to here, and the I2 will come flow through R3 and it will come here, and after this both the currents I2 and I3 are going to again combine or merge at this point D. Okay, so then it is like not only divides, it can combine also. Okay, so both the points can be mentioned as what, or I can note both the points B and D as what, node or junction. Okay, so the node or junction is where the current divides or combines. Also we can say it as, okay, current divides in the sense, so from looking from this end, so here also we can see. Okay, so both the currents are going to combine here. So that point also can be said as node. This point also can be said as what, node or junction. So point B and point D are what, examples of your junction or node we can say it as. Okay, so point A and C, they are not nodes or they are not the junctions. Fine? Yes. So now coming to branch. Branch is what? Branch means what? So we have a tree, so we will call the branches of tree, isn't it? So stem we have, after that branches will come, isn't it? So in that way we will be calling a branch is what? It is a conductive path. Conductive path. A branch is some path or like part of circuit, some part of circuit, or we can say a conductive path through which same current flows. So a conductive path through which same current flows. So that is what is what a branch will call it as. Fine? Is that okay? It is a conductive path from which through which the same current flows. Okay, so it has to be like that will call as what, a branch of the circuit. Okay, so same current should flow through that conductive path. So then we call that as what, some branch we call it as. Okay, so here we have one branch, here we have another branch. Fine. So likewise we have different branches for a circuit. Fine. Yes. So now coming to loop. So loop is what? Loop. Loop in the sense what? Looping. What do you mean by looping? Loop. Loop in the sense starting from a point and coming back to the same point. This is called as what? Looping. Fine. So starting from a point and coming back to the same point is called as what? Looping. So that is called as what? Loop. So loop is what? Any closed path in an electrical circuit. Any closed path in an electrical circuit is called as what? Loop. Is that okay? Yes. So any closed path, or we can say it as what? A loop. Okay. Starting from a point and coming back to the same point. Okay. So that is what is what? Loop or closed path we'll call it as. So any closed path in an electrical circuit is called as what? Loop. We call it as what? Loop. Okay. According to this examples, like in this resistor network, I can go for some loop as from where to where I can call as some loop. So starting from this Vs, okay. So let us start from this point A. So I can make loops. Okay, so what all loops I can make out? I can make some examples of the loop as what I can write it here. Okay, so I can have how many number of loops? Let me see. Okay, first loop what I can make is what, from starting from A and going to B. From B I can come to D. From D I can go back to A. This is loop 1. Fine? Yes. Now coming to second thing, I start from B. I can go to C. Then from C I can come to D. And from D I can go back to B. And this is loop 2. And third loop what I can make out is starting from A, going to B, and going to point C, and later on I can come to D, and from D I can go back to A. Likewise I can have what? 3 loops. Fine? So in this resistor network given, I can make out 3 of the loops. Okay, so loop is what? It is a closed path. It is a closed path in your electrical circuit. Okay, yes. So coming to mesh. Mesh is what? It is what? It is nothing but a loop only, but there is some difference. So mesh is what? It is an independent loop. So mesh is also a loop, but the different thing is what? It is an independent loop. Mesh is what? Mesh is an independent loop. Mesh, we call it a mesh. Mesh is a loop, but it is an independent loop. Independent in the sense what? So a loop which is not comprising any other loops within it. Understood? Understood or not? Okay. So a loop which has got no loop within it. So that is called as what? A mesh or independent loop. You can say it as. Okay. So from like in this resistor network given, so what all things, like we have named 3 loops. So what all are the meshes? Okay. So we have named 3 loops. So in that we have to make out how many meshes are there. Okay. How many mesh we can make out? So here let us see. So a loop within which we can't, like we shouldn't have any other loops. So such loop is called for independent loop. Fine, independent. It is not at all depending, like it will not have anything within any of the loop within it. Okay. So such thing is called for a mesh. So here this loop, last loop, which is that A, B, C, D, A. A, B, C, D, A loop. The outer loop. It is not a mesh. Why? Because this loop has got 2 more loops within it. Understood? Okay. So this outer loop has got 2 loops within it. That is why this is not a mesh. It is a loop, but it is not a mesh. So coming to first, first loop. A, B, D, A. A, B, D, A. So this loop is not having any other loop within it. So then this is a mesh. Correct. Okay, first loop 1 is a mesh. Loop 2, again it is an independent loop. Isn't it or not? Okay. It doesn't have anything like within it. Okay. There is no any other like loop within this loop 2. Okay. So that is why this is one of the example. Like this is one mesh. This is another mesh what you can make out in that resistive circuit. Okay, loop 1, loop 2, both are meshes, and also they are like they are loop 1 and loop 2 are not meshes, but loop 3 is only loop. It is not a mesh. Fine? Yes. So likewise we have to make out these terminologies or things which will be used while explaining your Kirchhoff'S laws. Okay, so now coming to some, like we will see some of the examples of some networks. Okay, so now we will be calling something as what linear network. Linear network in a sense, so linear device. So now we will call resistor as what? A linear device. So we will call resistor as what? Linear device. I have heard this while when teaching the Ohm's law. I have dealt with this. The linear network. Okay, so now here again we will see for your we had we had discussed this already. When it comes to Ohm's law, so Ohm's law says what? Ohm's law says what? Your current flowing through the circuit is proportional to the voltage applied. Isn't it? So when I increase voltage in terms of volts, the current increases in terms of what? Amperes or milliamperes will call it as voltage in terms of volts. It will be varying. So accordingly, if I vary the voltage in so much proportion of amount, the current also increases in the same proportion. So that will make me some of the points which will make a straight line characteristic graph. Okay, so this is your characteristics, voltage versus current. This is what VI characteristics we call it as, or voltage versus current graph I have put out of some network or circuit. Okay, so wherein or else also I can relate this to Ohm's law. So as I increase the voltage in some proportions, current also increases in the same proportion. So that will make a straight line characteristic graph. So a device or any of the circuit, okay, any of the circuit which gives straight line as characteristic. Okay, so which will give the straight line as what? Output characteristic graph. So such networks are called as what? Linear network. Linear network. Network is also called as what? A circuit. Circuit is also named as what? Network. Okay. So linear network. Linear network in the sense what? The voltage and current variations are what? In the same proportion. Such networks are called as what? Linear networks we call it as. Fine? Okay. Yes. So voltage. As I vary the voltage in the same proportion, current also increases in the same proportion. Such networks are called as what? Linear networks. Linear. Okay. So linear networks. Okay. So such a network is called as what? Linear network, where we have voltage and current relationship is what? It is almost same proportional. We can say it as. Okay. So non-linear network. Non-linear network is what? Exactly opposite of that, isn't it? Non-linear in the sense what? If I say something is happening to be like this. So something is happening to be like this means a network whose output characteristics is not a straight line. It is not a straight line, then such networks are called as what? Non-linear networks. So for example, see here, for this voltage, this is the current. For this voltage, this is the current. After that, for this voltage, the current is not varying in the same proportion. Here it has increased from 0 to this much. Here it has increased from this to here. Okay, for this one it is increasing from here to here, and after this, for this voltage, it is varying little bit. For this voltage, for example, for this voltage, from here to here it is not at all varying in the same proportion as here. Okay, so likewise we have a, so if I have to go if I go from this point to this point, if I go, so the current is remaining almost same. Okay, so it is not varying only. So that means what? For all the voltage variations, the current is not varying in the same proportion. So such networks are called as what? Non-linear networks. Understood? So also I can define non-linear network as what? The network or the circuit whose output characteristics is not a straight line. Okay, if it is not a straight line, so that indicates that voltage and current variations are not in the same proportion. Fine? Yes. So such networks are called non-linear networks. Now coming to bilateral network. When it comes to a network or a circuit, when coming to bilateral network. Bilateral in the sense, in bi means what? Two. Okay. So if for a circuit or in any of the network, so there will be two ways of current flow, isn't it? So if I have some resistor, so if I have some resistor here, so here I can make the current to flow in this direction, and also I can make the current to flow in this direction too. Okay, so current can flow in this direction, and also the current can flow in this direction too. Fine? Yes. So when it comes to both directions, when I consider both the directions, so bilateral network is some network wherein the voltage and current relations, okay, so the voltage and current relations are same in both the directions. If I apply some voltage here in this direction and current I flows, so then if I plot VI characteristic graph, so then the current and voltage relation is same as that of the current and voltage relation if I apply some voltage here and some current I flows in this direction. Understood? Okay, in this direction if I apply voltage and some current flows, the voltage and current relation is same as that of if I apply some voltage in the other direction and the current and voltage relationship is also the same as that of this side. Both the sides a network should give the same current and voltage relationship. Understood? So such networks are called bilateral networks. Okay, what are they? They are bilateral, means both the directions of the circuit, the current and voltage relations are what? Same. Okay, yes. Now coming to unilateral network. What is unilateral network is what? Unilateral. Uni means what? One. Unilateral is what? It is not same in the sense both the directions won't show the same current and voltage relationship. Okay, in one direction current and voltage relations are different. In the other direction the current and voltage relations are different. Is that okay? Yes. Now we'll see Kirchhoff's laws. So Kirchhoff has given us two of the laws. So first one is what? Kirchhoff's current law, and second is what? Kirchhoff's voltage law. Okay, Kirchhoff's current law, KCL we call it as. Kirchhoff's voltage law, KVL we call it as. Okay, so Kirchhoff's current law is also called as what? Node rule. Okay, Kirchhoff's current law is also called as what? Node rule, and Kirchhoff's voltage law is also called as what? Loop rule. Okay, fine. So we call it as what? Node rule. Node rule means what? Kirchhoff's current law, and loop rule means what? It is Kirchhoff's voltage law. Fine. Is that okay? Yes. So now we will come to the statement of your Kirchhoff's current law. So what he says about Kirchhoff's current law means what happens in current law and how we can make out the statement. Okay, so Kirchhoff's current law, KCL or node rule says us sum of currents entering the node. So node is what? It is a point where the current divides or combines also. Okay, fine. Yes. So sum of currents entering the node in the particular, if I consider particular node, so then sum of currents means total sum of currents entering the node is equal to the sum of currents leaving the node. Leaving means what? They are going away from the node. Okay, so sum of the currents entering which are going into the node is equal to the sum of currents which are going away from the node. Fine? Yes. So the sum of currents entering the node is equal to the sum of currents leaving the node or leaving that particular node. Okay, sum of currents entering a particular node is equal to the sum of currents leaving that particular node. Fine. So that is what is what? That is your statement of your Kirchhoff's current law. Sum of currents, if I consider some point or some node or junction in an electronic circuit or electrical circuit, if I consider some junction or node, so then in that particular junction or in that particular node, sum of currents entering is equal to sum of currents leaving that particular node. Fine? Yes. So in that way, I can consider, like I will be considering an example. I have mentioned some node A, or else small letter A. I will be considering. I have made a, like I have considered a node A wherein two of the currents are entering. I1 and I2 are entering the node. I3 and I4 are leaving the node. They are going away from the node, and these two currents I1 and I2 are going towards, or they are entering the node. I3 and I4 are leaving the node. So then with on application or applying Kirchhoff's current law, I can write summation symbol, isn't it? Summation of current entering is equal to summation of current leaving. So likewise, I can write with this example, I can write I1 plus I2 summation or sum of currents I1 and I2 entering the node. Fine. So sum of currents I1 and I2 are the two currents which are entering the node. So sum of currents is equal to entering is equal to sum of currents I1 and I3 and I4 are leaving. Okay. Sum of currents which are leaving this particular node A what I have considered. Okay. So from this example I will write I1 plus I2 is equal to I3 plus I4. Okay. And from law of conservation of energy, so it says that energy can never be created and cannot be destroyed. Okay. So energy, we can't create energy and we can't destroy energy. Only energy can be transferred from one form into another form. Okay. So in that way we can say the law of conservation of energy. We can't create energy, we can't destroy energy. Only what we can do is we can transfer the energy from one form into another form. Okay. So in that way, now here I can say the algebraic sum of currents is equal to what? 0. I can write it as. Okay. So algebraic sum of currents is equal to 0. I can write. Okay. And if I consider for a node, so algebraic sum of currents at this node is equal to 0. I can write it as. Isn't it or not? Okay. So I can write this equation is what? I1 plus I2 minus I3 minus I4 is equal to 0. I can write it as, isn't it? So this is how I can go for the Kirchhoff's current law. Sum of currents entering a node is equal to sum of currents leaving that particular node. Fine? Yes. So now coming to Kirchhoff's voltage law, it is also called as what? Loop rule, and Kirchhoff's current law is called as what? Node rule. Okay, so remember that carefully. So Kirchhoff's voltage law, KVL, and it is called as loop rule. So here what we'll be talking about is, so we'll be considering a loop. Okay, we'll be considering a loop wherein we'll be seeing how the voltage drop is happening with the applied voltage. Okay, so algebraic sum of EMFs. Algebraic sum of EMFs in any closed loop of a network is equal to algebraic sum of IR drops in that particular loop. Okay, so what happens here is the algebraic sum of EMFs. Algebraic sum of EMFs means, in the sense, I have taken an example. Here I have only one EMF which has been applied, that is V. Okay, so and we have two of the resistors R1 and R2, which will make two voltage drops V1 and V2. So V1 is the voltage drop across R1, V2 is the voltage drop across R2, and current I flows here. Fine? Yes. So the applied voltage. So algebraic sum of EMFs. In the sense, algebraic sum of EMFs in any closed loop. Okay. So this is a closed loop. Algebraic sum of EMFs. They are talking about if we have more number of voltage sources. Okay. Here I have only one voltage source. If we have more than one voltage sources, so then algebraic sum of EMFs in any of the closed network is equal to algebraic sum of IR drops. What is that IR drop they are talking about? IR drop is nothing but what? Voltage drop across your resistor. So voltage drop in the sense, what is V? V is equal to, by Ohm's law, what we have? V is equal to I into R. Isn't it? Voltage drop is also called as what? IR drop. Okay, voltage is equal to what? I into R. Isn't it? So voltage drop is also called as what? IR drop. Okay, so it is nothing but voltage drop across your V1 is equal to I into R1. Voltage drop across your V2 is equal to what? I into R2, because the same current flows. Isn't it? Only voltage divides. Okay, voltage V divides into what? V1 and V2. So we know that by voltage divider rule. Isn't it? Correct or not? Yes. So now this Kirchhoff's voltage law says us that the applied voltage or sum of the EMFs applied in a closed loop is equal to the sum of algebraic sum of voltage drops or IR drops. Is that okay? Is that clear? So applied voltage or algebraic sum of EMFs applied is in a loop is equal to the algebraic sum of IR drops. So that is our statement of Kirchhoff's voltage law. Okay. So which says that sum of EMFs is equal to sum of EMFs is equal to summation of IR drops. Okay. Summation of IR. Okay, so those which are happening. Okay, so what, like by this way, so I can write V, applied voltage V is equal to, that is your EMF. Only one EMF source pair we have. So it is V is equal to IR dot. Summation of IR dot is what? Here the current I flows here. That means what? Voltage drop across your V1 is equal to I into R1. Yes or no? So I into R1 plus I into R2. That is across your R2 resistor. This is the voltage drop. So finally I can write it as what? V is equal to V1 plus V2. I can write it as. Fine? Yes. So this is about your Kirchhoff's voltage law. Okay, the applied voltage will be in a loop, means sum of EMFs applied, sum of EMFs applied in a closed loop or closed network is equal to sum of IR drops will voltage. Okay, so this is how we will be going for your Kirchhoff's voltage law or loop rule and Kirchhoff's current law node rule. Okay, so Kirchhoff's laws are very important when it comes to analysis of a complicated or complex circuits. Okay, so we will use Kirchhoff's law plus Ohm's law to solve the complicated or some complex networks. When it comes to very simple networks, we will use only Ohm's law to solve or to analyze the circuit. Okay, so this is all about today's class.